Part 1. Vivado Design. Adding Zynq IP to the block design. With our project set up, let's add the Zynq UltraScale IP. You'll see a banner appear at the top of the diagram suggesting to run block automation. Click on Run Block Automation, select Apply Board Preset, and click OK. This process configures the IP with preset parameters that match the ZCU 104 board layout. AXI GPIO for user LED control. Add an AXI GPIO to the block design to control the 4 user LEDs. And then, set its direction to all output and configure the bit width to 4 bits. Expose the AXI GPIO output as an external port, rename the created port to LED control. During I/O planning, these ports will be assigned to the correct pins. AXI GPIO for user dip switch. Next, add another AXI GPIO for reading the user dip switch. Set its direction to input and configure its bit width to 4 bits. Make the input as external port and rename it to dip switch. AXI GPIOs for more practice. To gain further practice, add 2 additional AXI GPIOs. For each of these, set the bit width to 32 and change the direction to output. Then, add another AXI GPIO, set its bit width to 32, and configure its direction to input. For some additional functionality, let's use these GPIOs for simple arithmetic. Add an adder IP block to the design. Change the adder's input width to 32 bits and remove the clock enable option. Connect the outputs of the first 2 AXI GPIOs to the inputs of the adder. Then, route the output of the adder to the final AXI GPIO. At this point, we can let Vivado handle the connections automatically. Run the Auto Connection Automation feature. This will automatically add a processor system reset and an AXI interconnect to the design. Vivado will then connect the Zynq IP master port to the AXI interconnect and from there to all the AXI GPIOs. For this design, only one master port is enough for ARM cores. Double-click on Zynq IP and remove the second high-performance master port. Let's highlight the clock and reset signal for better vision. As you can see, the whole AXI network is running with the same clock and reset signal. Inside the PS section of the Zynq UltraScale Plus, multiple PLLs are available to generate and manage various clock signals. For instance, one of these PLLs can be configured to provide a 100 MHz clock signal to the programmable logic for synchronization and operation. You cannot directly connect the PS reset to other peripherals. The processor system reset IP block is specifically designed to provide a synchronized reset signal aligned with the AXI clock. It takes the reset signal from the PS, synchronizes it with the provided clock, and then distributes it to all connected peripherals. Now we can validate the design. It will automatically assign addresses to all connected peripherals. Addresses of connected peripherals. Once the design is validated, Vivado will automatically assign addresses to the AXI GPIOs. This process, known as memory mapping, allows the ARM cores, acting as masters, to access all connected peripherals using their specific addresses. For better understanding, you can change the view style to Addressing View in the Vivado design. For example, in this design, the processing system has access to all AXI GPIOs through their unique addresses. Now we are ready to proceed to the synthesis step. Add the top-level wrapper and let Vivado automatically generate and manage it. Run the synthesis design and wait until it's finished. Assigning the I/O ports. Open the synthesized design and open I/O ports. Assign the LED pins. Based on your board datasheet, assign the appropriate pins for the LED outputs. These should be connected to the specific pins listed in the board's documentation. Connect the dip switch pins. Locate the user dip switch pins in the documentation and connect them accordingly. Once the pins are assigned, save your I/O connections as an XDC file. If you're working with the ZCU 104, I've also shared a pre-configured XDC file in the GitHub repository for convenience. With everything set, you're now ready to generate the Bitstream. From the left-hand toolbar, select Generate Bitstream and wait for the process to complete. Exporting the hardware. The last step in Vivado is to export our hardware design for use in Vitis. Go to File, Export, Export Hardware, and make sure to check the Include Bitstream option. It will generate the XSA file for us. Part 2, Vitis Design. Create new project. Launch Vitis IDE and create a new application project. When prompted, select the XSA file we just exported from Vivado and create a new platform. Complete all the steps and use the Hello World template as our starting point. This gives us a basic structure to work with and ensures that our development environment is set up correctly. Provided driver code. You can download the code from our GitHub repository. Simply copy the entire code and replace the content of the Hello World file. Now, let's take a closer look at the different sections of this driver code. Address definitions. The code defines macros for the base addresses of each AXI GPIO peripheral. Each GPIO module is assigned a unique memory address. These macros are derived from X parameters header file and correspond to the addresses in implemented hardware design in Vivado. X parameters header is a very important file, and it contains the base addresses of AXI peripherals mapped from Vivado. You can find the address of different slave elements in this file. Zil out and zil in functions. At the core of our code, there are two key functions. Zil out 32 sends 32-bit data to a specific hardware address. This is how we send control or data values to the peripherals. Zil in 32 reads 32-bit data from a hardware address. This is how we retrieve information such as the state of the DIP switches. Let's take a closer look at these two functions to understand how they work. You can find the implementation of these two functions in Zynq IO file. As you can see, zilout defines a volatile pointer, assigns it the address of a peripheral, and then uses that pointer to write a value to the specified address. Similarly, zil in defines a volatile pointer, but in this case, it reads data from the peripheral's address using the pointer. To summarize, for each peripheral connected to the ARM processor or the AXI network, we assign a specific address. Using a volatile pointer, we can easily perform read and write operations to and from these addresses. First part, interfacing with the adder module. The first part of the main code interacts with the adder module implemented in the PL. All the transactions at the first part is done with the pointers. Here, the AXI GPIO serves as an interface, allowing data to flow between the processing system and the programmable logic. We write values to the AXI GPIO connected to the adder. Then, we read back the result and display it in the terminal. Second part, DIP switch control in polling mode. In the second part, the program reads the DIP switch inputs in polling mode. This means the system continuously checks for input changes in a loop and applies corresponding adjustments. Each of the 4 DIP switch bits controls a specific LED behavior. Bit 0 controls the shift direction. Toggle this switch to change whether the LEDs shift left or right. Bit 1 adjusts the speed of the LED shift. When set, the shift slows down. Bit 2 acts as a pause button. Setting this bit stops the LED shifting until it's toggled back. Bit 3 turns all LEDs on or off. When set, the LEDs are off regardless of the shift pattern. Now that the code is ready, it's time to build the project and run it on the ARM core. Ensure your board is connected to the PC and the boot mode is set to JTAG. Use the Launch Hardware feature in Vitis to load the Bitstream and application onto the board. Once the program is running, first, you'll see the results from the adder printed in the terminal. The program will pause and prompt you to press Enter. After pressing Enter, the LED control section begins. Here's what to expect. Flipping the first switch changes the LED shift direction. The second switch slows down the LED shifting. The third switch pauses the shifting. The fourth switch turns off all LEDs.